Number 89 here looks like it's taking us back to some of our definitions of limits and continuity and differentiability back in Chapter 2 and Chapter 3. So what do we have here, guys? The limit as x approaches a of our function is equal to f of a. Now this is kind of what would happen in a quote-unquote normal case, guys. If you just had some random curve located right over here, and notice I've drawn a curve that's continuous and differentiable. In order for this to happen, at a particular spot right here, which I'm going to call a, the limit as x approaches a is a y value that we're approaching from both the left and the right, and if that's equal to the actual value of the function here at a, which we'll call f of a, that means that our left-hand limit, our right-hand limit, and the value of the function all agree. Some cases where that might not happen, guys, would be something like a hole, okay, like this. Now in this case, the left and right-hand limits do agree, but if I put a closed dot right down here, that limit does not equal the value of f of a. And then of course another counterexample would be if the curve did this on the left and this on the right, and one of these dots was closed and the other one was open, now your left and right-hand limits don't agree, so the two-sided limit doesn't even exist. So these would be counterexamples. This is kind of what we're actually talking about right here, guys. Although, you want to be careful. Just because I drew one picture right there that in my mind satisfies the statement, that doesn't necessarily mean that's the only picture that satisfies that. So we still have to be critical thinkers as we go through this problem. So let's see what's true here, guys. Which of the following has to be true? A, the function f is continuous at x equals a. Well, I hate to ruin all the drama, guys. The answer here is A. Now, I'll come back and talk about the next four in just a second right here, but what we are dealing with right here is the actual definition of continuity at a point. The left-hand limit has to equal the right-hand limit, and both of those limits have to equal the value of the function itself, f of a. This is the very definition of continuity at a point, so I'm pretty darn sure that A is the answer. What else is going on right here, guys? B, f is differentiable at a. Now, this is what I was talking about just a second ago. I've drawn a picture right here that certainly looks like this function is differentiable at a, and I could draw my tangent line right there. But that doesn't mean that it has to be. I could have drawn a curve now, guys, that did something like this, and then all of a sudden takes this weird turn right out here. Now in this case, everybody, if this is a and this y value here is f of a, this still satisfies this definition here. Left and right hand limits are still equal to f of a, but a tangent line does not exist at this weird sharp corner right there. Therefore, this second function that I've drawn right here for part B provides a counterexample. B doesn't have to be the case, although very often when you draw it quote unquote normally, it will be. Okay, how about part C? For all values of x, f of x is equal to f of a. That's weird. That just kind of implies that your function has to be a constant. Well, what I drew here in A, which I thought was right, and what I've drawn in B, is a counterexample to that, guys. The function is not always equal to the same value. That was kind of a weird one. So that was C, and that's why that one's not a right answer for number 89. D, the line y equals f of a is tangent to the graph of f at x equals a. Well, again here, guys, y equals f of a is a horizontal line going right through here. That's not a tangent. So there's a counterexample to D. And how about E? The line x equals a is a vertical asymptote of the graph, not in what I drew there in part A. So I think I've got counterexamples to B, C, D, and E, and that just kind of verifies my thought here that A is the correct answer for number 89.